So I think we'll try to make a start. So welcome everyone. At ANU, we acknowledge and celebrate the first Australians whose traditional lands we gather today and meet. We pay our respects to the elders past and present. Today we have the great honour of introducing Professor Anna Wåhlin from the University of Gothenburg. Anna has research interests in ice-ocean interactions, and particularly ocean undersea processes, boundary layer processes, and wanting to understand the sort of fundamental physics that govern those dynamics. Anna's approach is quite unique. It's, in addition to sort of running and leading very large-scale observation endeavours on board icebreakers and sort of going out to those high latitude and remote regions to actually study those processes in situ. Anna also employs idealized laboratory experiments to try to get to the sort of nitty-gritty of those processes in a way that can't be done by any other means. And that's what actually brings Anna to ANU for this sort of next little bit. This initial 6-week visit that Anna's making is to use the laboratory in the climate and fluid physics lab to actually study some the effects of rotation on sort of the melt rates and the ice-ocean interaction processes in our lab. So Anna's has been co-chair of SOOS, the Southern Ocean Observing System, as well as the Scientific Committee for Antarctic Research, SCAR, and is currently an editor at JGR. And it's my great pleasure to introduce Anna. So has been running observation programs on spending a lot of time on the Nathaniel B. Palmer, and that's probably what we're going to be hearing about today by the looks of it.
Great.
Thank you, Anna.
Thank you very much for thank you for a very nice introduction, and thank you for allowing me to come here and do these really interesting lab experiments. I wish I was, if we had been 4 weeks ahead in time, maybe I could show some results, but we are still very much in the pilot stage. But you're all welcome to come down and have a look in the lab anytime. Yeah, so I wanted to talk a little bit, that is correct. Most of these results come from the NB Palmer, and we have also been quite a lot on our own, the Korean icebreaker. And this is results mainly from 2022, but also a little bit from that we got this past season, 24. And yeah, the title is Swirls and Scoops, and I will show some of the images that we get from the underside of the ice that are really fascinating, and we can't really make sense of them also. And there are many people involved. This is just a few, and are we taking off? So this is just to mention a few of them, but they're big field programs like this have really many people involved, and they're all equally important, I think. So yeah, I know many of you are well aware of this kind of background. We are interested in the ice shelves because they are melting. Some of them are melting quite fast, and they have the potential to impact future sea level rise. And there's in particular one region here in the Underside Sea where it's very red, so they are melting rapidly. And the reason for this is believed to be the ocean. And here is a map of the Underside Sea. So typically you have some quite warm, salty ocean currents coming in and accesses these floating ice shelves. And typically it's in where you have deep troughs, there the water can enter, and then you have meltwater flowing out like this. So this is a very typical image of a shelf system like this. There are others also in Greenland that look similar with similar current systems. The problem is that we have some data out here. You can access that with ships and you can put moorings in the ocean, but it's very much like a black box inside the cavity. We can measure what goes in and what goes out, but it's really tricky to get data from inside it. You can drill a hole. The ice is 300 to 500 meter thick, so it's quite an effort to drill holes, but they are very good because then you can place moorings inside the ice, so that's nice. And you can have an ROV, which is the robotic vehicle that is connected via a cable, so then you can remote control it, and you can get some very good samples. You can get close to the ice and get photos, but they are quite limited in range. So if you want maps of what goes on, if you want a bigger view, you have to have an autonomous underwater vehicle. And this is a very simplified view of the current system. This is very much based on observations from outside the cavity. So typically you have an inflow inside the deep troughs like this, and then you have a warm salt water leading up, because this is all rotating. It typically leans up on the bank and then flows into the cavity, and then you observe on the western part outflow like that. So somewhere this warm water gets in and somehow it meets glacial ice and then it flows out again in principle. But the fuzzy part here is where does it meet the ice and what processes happen when it meets. So the vehicle we have used is called RAN. It's a Hugin. It says lots of people online at wrong address. Yeah, it's a. We haven't built it ourselves. We bought it. There's a company called Kongsberg that manufacture these, and they have made many vehicles for the military, and they also make for a company called Ocean Infinity that are hunting for wrecks and missing airplanes and stuff like that. So we have serial number 58, so there's been quite a few. But when we bought it, we were the first academic department to get one. So the good thing with having many is that they are well tested. So this is a quite reliable vehicle, in my opinion. They have good systems that are like navigation. That's a typical example of where you need many trial and errors, and you get that if you have many. But ours is a bit different. It's custom made. It's a bit bigger than other Hugins, and that is so that we can get many sensors fitting onto it. And it has also got navigation, upward looking navigation and upward looking systems, specially made for targeting the ice. So it's depth rated to 3,000 meters, and you can travel up to approximately 300 kilometers on one battery charge. And the cruise speed is about 4 knots. And all in all, we had 38 sensors on it up until a year ago. A year ago, approximately, we lost it in Antarctica. We were doing an under ice mission from Aron, and it all went really well, and we were starting to be relaxed within 6 missions, and then on the 7th mission it never came out. We don't know what happened. We have some hypothesis, but we don't know until we get it back, which we will probably never get it back. It's under hundreds of meters of ice, and if it gets out, it's quite likely it will break in that process. But it floats, so it's possible. Maybe someone will find it somewhere, and I hope they call me. So, but those are the risks that you take with this. It's of course a huge investment, but we are happy that we have got some support now. So we are actually in the process to replace it, which is unfortunately a long process. But so the special thing, the most unique data, in my opinion, is that you can get high resolution maps of the underside of the ice. So most of the data that we have of the ice shelves in Antarctica, they are based on radar. And radar is electromagnetic waves, and they are quite good. They scatter in the ice, which means that you get information from the ice itself. You can see layers in the ice and so on. But it also means that you have a large footprint down here where you are supposed to get the shape of the base. So you're not quite sure what you're getting since the footprint is so large. Multibeam sonars that we have on the AP, that's sound, and sound has the property that it does not scatter in water. The signal travels nearly perfectly until it scatters off something. And in this case, it's ice. So the footprint is super small. It can be, depending on how close you are, you can have a footprint that's 2 centimeters. And that also means you can have many of these waves, these signals going out. So the one we have looking at for it has 450 beams. So again, if you spread them evenly, you can have a resolution of less than a meter in the ice shelf. But again, the drawback is that you get only the surface of the ice. There's nothing beyond that. You don't know what type are the fractures inside the ice. Is it mushy? What is it? So the best thing is to combine the two, radar and multibeam, then you get good information. And multibeam sonars, they are used commonly. Every modern research vessel has one, and they are used to scan typically the seabed. And when we started this, no one was quite sure if it was going to work on ice, but the results show that it has worked quite nicely. So when you do an under ice emission with the AV into an ice shelf cavity, the typical way that we do is that you park the icebreaker somewhere part away from the ice shelf cavity where it's safe, not too many icebergs, not too much sea ice, and then you get prepared to launch, and you put it into the water and tell it to dive as soon as possible down to the seabed. And when it's at the seabed, that's the safest place to be for an underwater vehicle. It's free from ice, and when it's close enough to the seabed, it can also aid navigation by something called a DVL, which sends out sound signals and listens a little bit like a bat to the changing frequency. So then it has very good navigation. And then after it has gone into the cavity, it goes up to the ice and does service near the ice. And when it's near the ice, that too is a quite safe place to be, as long as you know a bit about the ice, that it's a solid ice, and sea ice, for example, is moving, so that's not so good. But the ice shelves are quite safe, actually. The only thing is that when you have something going wrong, it goes really wrong. So that's but in principle, they are safe spots to be, because if you go near enough, you can have this upward-looking DVL that helps with navigation, so you have good navigation. But every time you dive, you introduce the error in the navigation. So about 50-meter error going down, and then you come in, and then another 50-meter going up. And then you go down again, and then out and pick up the vehicle. And during this time, so you can communicate via sound from the vessel, but when it's inside the cavity, there's no communication. And this takes typically 24 to 28 hours. So when it's inside the cavity, normally we tell them that you can do other projects with the ship. You just turn up here on time. And if it turns out, yes?
So if you have no communication with the, when and where does it know it needs to ascend?
It's programmed beforehand.
Also, so you have to have an idea of what the shape of the cavity is.
Yeah, exactly. So that lowers the risk. The more information you have about the shape of the cavity and fractures and all that, every information lowers the risk. So typically what we do in the high risk missions is to start with a mission that's only going near the seabed and try to get more information about what goes on up there, and then go out, take it back and build a map based on that, and then go a little bit further. And we can also go survey out here and then take that back and then go a little bit further. So if you want to do it properly in a completely unknown, or where you have only got maybe remote sensing data from satellites, that takes many days to build up. I forgot where. So this is Dotson Ice Shelf in the Amundsen Sea, and the black lines here, they show all the missions that we did in 2022. So we have put it into the water somewhere out here, and then, for example, this black line shows it going in and then doing a survey, this lawnmower pattern, and then going back out, and then being picked up by the ship. And we had 5 or 6 of these missions, and we tried to get, when you do a lawnmower pattern like this, that is in order to get a map of the ice. This is the standard procedure when you map the seabed, and we have just copied that and turned it upside down. And you should try to estimate how far from the ice you are, so that you get some overlap. When you go one way like that, you should have maybe 10 or 20% overlap going back, because that gives you immediately a quality control on the navigation. If you see a feature here and then it's here, when you go back, then you know you have a problem with the navigation. And this, in this case, we had also got a hole drilled here. So there was a radar placed here, and there was a mooring also. So we could check, have some double checking there. So this is an example of what you get from the sensors that measure temperature, salinity, and dissolved oxygen. This shows meltwater fraction. I don't know why it's so blurry, but never mind. Blue is small meltwater fraction and red is high, and you can get that by calculating. If you know what you start with, then you know that, okay, you assume that we have melted ice. The water gets cooler due to loss of latent heat, but also a little bit fresher. And that's called the Garde line, like you showed some nice plots earlier. So based on, if you calculate how far you are from the Garde line, you can get the meltwater concentration. So this plot, so this is all quite near the ice. This shows that we have low meltwater concentration here, medium here, and we have some quite high concentrations in the west where the outflow is. And this shows velocity near the vehicle. So this is velocity between 50 and 20 meters below the ice, approximately. Here it's a few centimeters per second, and at the outflow we have up to 20-25 centimeters per second. So that's quite fast for being in this part of the world. And the dots out here, they are from the ship-based system. So this sort of confirms the overall view that we have, that you have the deep inflow here that we can't see, it's not near the ice. And then we have the outflow of meltwater over there. And there's also a surface current, a current flowing along the ice shelf that is a totally constant current. So this is no big surprise, but this hasn't been confirmed until this survey. You could not be quite sure if this current that you see here is actually coming from inside the cavity. It could be this coastal current being accelerated by additions of meltwater. So this was the first time we could connect it really to inside the cavity. So that was nice. So if you look at this part here, now we are going to look at the ice, what it looks like. So this region here in the west has fast flowing water and high meltwater content, and it's also quite warm. compared to other water at the same level. That is because when you melt ice, you pull up the heat energy from below. All the other water here is winter water that is rather cold. So you actually strangely add, the meltwater outflow is a little bit colder than what is over here. And there the ice looks like this. So this is about 5 kilometers, this area here, and these things here, they are fractures in the ice, and you can see them from space also by satellite, so they penetrate through the entire ice. And you can also see these structures here, erosional patterns. That's what the geologists said when they saw them immediately. It looks like erosion. They are parallel to the main flow. So this is probably caused by water moving quite fast underneath the ice. And then there are some funny shapes that we don't know what has caused these. They're shaped like teardrops or blue mussels, and they were everywhere here in the West. We had over 100 of them. Here we could count over 100. And if you zoom in, here is an example of them. They look very similar in shape, but different size. The biggest ones are a few 100 meters long and 20 meters deep, and then there are tiny ones that were only like 10 or 20 meters long and maybe 1 meter deep. And we really don't know what caused them. We have a hypothesis, and that's one of the things that we were hoping to maybe see in the lab, if this is true, that this could be due to Ekman veering of the flow underneath the ice. The Ekman spiral under the ice looks a little bit different compared to the one when wind blows over water, but it's sort of similar. So this is the shape of that, and they are a little bit similar, and the tip here on every of these teardrop is about 45 degrees, which is also what you get from the Ekman spiral. But we have no data inside them. You would need to have something measuring here in order to really know if we are right. And then if you look further east, where we have quite slow currents and low meltwater content and comparatively cold water, and also, I should say, a comparatively small ice-based melt. Over here we have, based on satellite data, between 1 and 2 meters per year. Over here we have 15 meters per year. And that 15 meters per year, that agrees quite nicely with what if you take a simple turbulence model and apply that to the initial conditions that we measured, you get the same rate. So that was quite nice to see that the free equation model works. So over here, it looks quite different from in the West. Here, we don't see any of those big streaks or erosional patterns. Instead, there is like layers in the ice and very sharp regions, very sharp boundary between, like here, this is thinner, so here we have had some melt, and over here is thicker and there's no melt, and the region is razor sharp between them. There are several of these features where we clearly see melt and then no melt right next to it. And also many of these banana-shaped things like that, many round things. The melt patterns seem to often end up with a fingernail-shaped thing. And if you look overall, so this is north upwards, and this purple, that's high melt, this is thinner ice. So overall, if you squint and don't lose yourself in the patterns, it's higher melt nearer the ice front, which is to be expected if you think that also the surface water has some influence on the melt. And there's a new study from RSES where they have also observed that. So I think that's quite plausible. And this is the slope of the ice maps of these regions, but showing the slope instead. So red is about 45 degrees. So you have large regions where it's completely flat, more or less, and then some very steep steps to the next. We know this melt, this ice has been gone away, so to say, but we have only a snapshot in time. So we try to think about this as a longer for ocean melt. But we honestly don't know the processes here. It's not turbulence. We think the turbulence, that's what you see in the west, where you have the strings and everything. But this is something different. And I'm hoping that we can maybe find the explanation here in the lab. I haven't seen any models that can explain it either. And we suspect there is if you start to have a small shape in the ice, that will steer the water so that there's a tendency for this shape to become deeper and deeper, something like that, or that the rotation somehow confines the flow. But these are so sharp, and it's like 10-meter melt, and regardless what process you have, if you melt 10 meters of ice, that's going to take some time, and the water does move. You have tides, you have everything. So it's really hard to think of a process that could create such a sharp step here if it's not a combination of ice shape and water flow. Then also we have fractures. If you look here and here, those are examples of fractures. So we also got a closer look at them. This background here is the remote sensing product, so you can clearly see each fracture from above as well. And because we can see them from above, if you look at old remote sensing data, you can trace them back in time. So this one here, for example, was formed 1997 to 2001, and there's some. This one is even older, from 1990, where we had the first satellite records. So this one was over 30 years by the time it reached this part of the ice. And the older fractures, they seem to be, you can clearly see that they are sort of worn down, probably by ocean melting. They are much broader and much smoother at the base. And then there are some new ones. This one appeared in 2017. And it has a much sharper boundary, so that's a 90 degree. This one is going straight up like that, and no big signs of melt on it. And then if you look further east, we have some really new fractures. This one is disappearing into the ice, so that one is just forming now, and also that is razor sharp. And yeah, so if you look, if you take a section across like this, you can see them in a profile, and then it looks like this. So the old ones, they are worn out, smooth. Then we have this strangely flat ice, and then we have a smooth fracture, and then there's a young one where you have a vertical. You see a gap there, and that's not because there's no returns, so the signal has just gone up. So we don't know exactly what it looks like here. But this one know for sure, they are these structures, you can see. And then there are also, in the old fractures, you can have these, again, some kind of indentations into the ice. We don't know what either is. I hope maybe we can see them in the lab again. But probably, we are guessing they're formed by outflow here. Maybe if this fracture gets squished together occasionally, maybe they can form these melt patterns. So to summarize, we have this is what we had learned. It doesn't look like we thought the ice. We see traces of inflow, surface near inflow, or inflow near the base of the ice. We also see the deep inflow, but that has no apparent effect on the ice here anyway. And then we see the strong outflow, and this is creating a sheared, a smooth ice base, and in addition we have these blue mussel shaped. And now we proposed the Ekman for this shape, and it's not yet disproven, but this one more we propose maybe this is intermittent convection creating this sharp, but more and more we think about it, we don't really believe that, because even if you have convection, the water will still move a little bit, but it's super sharp boundaries. So yeah, I can just show you a little bit what we did last season when the season we lost it. So this is a zoom in of the eastern part where you have the plateaus. This was in 22, and this was what it looked like in 24. So in those 2 years, the ice moved 900 meters, so you have to pull it back 900 meters to, but this is the same ice. And first, it looks exactly the same. We thought we had to double check that we had the same data set, but if you look closer, you can see that this one here is deeper, and this trough, this channel has become a bit wider, and this thing here is both deeper and wider. So there are some small changes, even if it's very, yeah, we were very surprised that it looks so similar. And this is further south, where we also have that mooring, and also here very similar, but this channel, the air has definitely become deeper, and this one has suddenly appeared. In 22. And if you take one minus the other, if you take 24 minus 22, you get an image of the ice melt, a map of the melt in those 2 years. So most of this is, because they are so similar, it's very small, but 1 meter to 2 meters. But there's also some areas where you have a huge melt. This is 20 meters over here. So it seems this depends a bit on how you do that translation. The ice velocity is quite coarse, and if you move it or even slightly wrong, you will get a mismatch. So you can have dark red areas, but then there will also be some blue areas. So there is a bit of we're working with that method. How do you do this correctly? But I think we can say for sure, even without having the method finished, that it's for sure there are regions of high melt. So the thing you measure from satellites, 1 to 2 meters per year, that is could be a bit of this background, but it could be that this background is actually mostly divergence in the ice. Those are the same order of magnitude, but it's definitely made up of small areas with high melt as well. And when you look from above, you don't see those, you just see the average. And yeah, so now I'm here, and we have started to have some fun in the lab, and please feel free to come down. It's just we are only just getting started, but I think we see already some features at least that are interesting, and we have a method. Ola is the designated photographer, he's there, and we have a method to get structure out from many. If you photograph this, take 100 pictures at different angles, you can convert it into data of that surface. And we are here now, we are looking at the methods and trying to get organized, and this is the stuff we are doing now. And then we will move on to having a sloped surface like this. This is all in the spinning tank. And then also to have a flat pack of water. And the idea here is that you get maybe something similar to a plume on the sea floor that has entrainment and so on. And those are quite strongly steered by topography. So maybe this one will too. But we already see patterns also with this one, spiral patterns moving up, which could be an artifact, so not say too much. So to summarize, the strong velocities at the outflow, that gives strong erosion, smooth surface of the ice, and these droplet shapes presumably caused by Ekman transport at the boundary. That's our only hypothesis. Anyway, would be very glad to see if someone comes up with something else. And the calmer conditions in the rest of the cavity, they seem to promote this stepwise or very local melting, which could be due to some convection process, double diffusive convection, or to an ice ocean feedback where the ice sheet steers the ocean currents. But the short version is, I think that there is some very exciting and unknown fluid mechanics inside the cavities. And with these new methods that we are starting to get, we can now finally address them. Yep.
Thanks, Emma. Got questions for Emma?
Can't help but be curious, what is your leading hypothesis that caused the view that you need to get,
It's the leading hypothesis, I think, is that we did something like this. I talked about the DVL. To get good navigation, you need to be not far further away from the 80 meters, roughly, within 80 meters from the ice. And then you put something called a safe distance, so it always detects how far it is from the ice. And then the safe distance was 50 meters, say. And then if it feels the ice coming down, it will adjust so that it's always 50 meters, not more. And then it adjusts its depth like that. And then if there's a fracture, it will feel that it's clear to come back up. And then it adjusts back up. And then it can be a bit tricky because these fractures are, some of them are a kilometer wide, but some are only 200 meters or so. And then if it's adjusting up, it can be sort of stuck, not being able to dive down. Or it could be that it's detecting something in the water, something like this. That's our hypothesis. Yeah. In this, if it was this, that was due to the human error that we put the depth, the target depth, not wise. Yeah.
Right.
Related to that, maybe, is it possible, logistics aside and cost of logistics aside, would you go to put an antenna down one of those drill holes? If you said you had a drill hole through the ice to help communicate with the AUV while it's under?
Yeah, you could. I think that's a brilliant idea, and we have been toying with that. You can have not a radio antenna, but you can have it communicates everything via sound. So you can put a transducer if it's thin enough, if it's small enough. Those holes aren't so big, and then you can program the vehicle to let it know that that transducer is at this position, and that will help navigation as well. So that's a very good suggestion. Yeah.
Yeah, are you able to quantify or at least estimate like how much of the melt of the total ice shelf occurs in these interesting features you see versus say at the grounding line or like the low background rates you see?
I think it's small. I think all melting is small compared to what happens at the grounding line. But of course, at the grounding line, we have even less data. But the water is warmer at the grounding line, basically. So it's an order of not quite an order of magnitude, but you expect the melting to be equally large. But in an ice shelf like this, the grounding line is very far in. So it would be nice to do the maths there, actually. I don't know. I suppose that's the short answer. Yeah.
Does the AUV is that able to get an estimate on ice density as well as its
You could get ice density. It's based on pressure, so we know the pressure where the ice surface is, and if you combine that with satellite altimetry, you can get the density. You know how far down it sticks, and then you know how far up it sticks, and then it's quite easy to get the density, but I don't think anyone has done that yet. This data set is open. We published a paper last summer, so all that data is in connection. If you click on the link, you should get all the data, and it's so much data. So anyone who want to, that would be a great thing to do, I think, with the data, but so far no one has done it as far as I'm aware.
How large are the tides? And do you see the shelf moving with the tides?
So a meter, roughly, I think, at the spring tide. And when you do the satellite altimetry, you have to be really careful about adjusting for the tide. But here, when it comes from below, you don't have to be so particular, because there you have a much smaller error, because it floats up and the pressure is the same. The distance to the ice is the same, if you understand.
Yeah. Okay. So they are moving with the tide.
Yeah.
You do see teardrop-shaped things on beaches, for example, when there's a disparity, right? There's a seaweed or something, you get that teardrop shape behind it, which presumably on a beach is caused by wind. So could that be caused here just by flow going past the disparity in the ice?
Maybe. You mean like if there's a harder ice in one place, a softer in the other? Not impossible at all. But it's a bit strange that they are not symmetrical. They are like blue mussels. They bend slightly. That's the only. So there's something else maybe too. But yeah, we have discussed at length. I mean, there was a big group working with this first paper that came out, including glaciologists, and we discussed this a lot. Can this be ice? Can it be due to ice? But they kept saying that it's homogeneous, the ice, because it's built under such high pressure. But I'm starting to because this ice, most of it melts away at the grounding zone, and it's not that old. This ice is maybe 400 years old or something, but it's the youngest ice that we keep, and it's I don't know, 200 years for it to move out. So maybe what we are seeing here is something that actually formed from snow. I mean, it's not, maybe it's not so homogeneous, but they say.
We had a question from Maddie.
Yeah, we got one question from my audience. The question: did you observe any notable difference in currents near the rifts?
Good question. Let's have a look. Good question. That's really, so here are, for example, maybe there are two rifts here. I don't know if they see where I'm pointing. There's a rift there and one there. I think it looks like there's something. This is 50 meters below the ice. So, but we do have some streaks where we went 20 meters, where we also passed below rifts. It's definitely worth. Was it Madi? But yeah, she is welcome to download the data and have a look. Yeah.
Oh, yeah. Sorry, Louis.
There's all these interesting fractures in the ice sheet itself. What is their relationship to the stress field? Are they tensile cracks or shear?
It's here. It's I don't know this terminology, but the ice is flowing a bit faster here compared to here. Over here, it's grounded and it has an input. There's ice flow from the side. Yeah, so it sort of flows here, and so here there's some stress in that direction. There might be other vertical as well, because somewhere out here it's stuck, and here it's floating. And then there's some interesting fields over. I should have included but I did not. Over here it's quite interesting because here you have two sources merging. So the main source is flowing northward. And then you have one source here and one there. So here you have a quite interesting stress field as well. And also the same there that it could be vertical somehow. So no one has really looked carefully at that either. That's
That was just
also
interesting. So it's homogeneous, but obviously once you start forming it, especially if you've got fractures, then your stress field is going to really change the property potentially as it flows.
yes, that's a very good. Maybe we can learn something. I don't know if we can learn something here where it's forming, and also maybe looking because we came back here 2 years later. Maybe you can. But unfortunately, we only have the surface. There's nothing here. We do not have any radar or anything, so we don't have any more information. How much are those? Should I answer that?
Yeah, I'm trying to read it. The localized.
Yeah, I agree. The question is how much are those localized high changes in drops reflective or more moderate melt rate acting on steeper sloping wall?
How much, or can I read it somewhere? Or, there we go. Yeah. Localized high changes in draft reflective of more moderate melt rates acting on steeper sloping walls.
Things within the fractures.
Oh, within the fractures. I don't understand the question. Sorry, I don't. Do you understand?
I'm not sure what draft reflective is.
Could you rephrase it?
Is it possible for me to speak to you directly?
Like when you have those swirls, it goes like this.
Yeah.
And how much of that might be because these walls are melting faster than the slower that was my answer.
Yeah, in that case, the answer is easy. We don't know because for most of them, we have only this one snapshot, so we don't know anything about melt rates really. We only have the results of the melt. We have no observations of it while it happens, except for this here. And yeah, but I don't know if that answers the question.
Is that difference between 2024 and 2022? Is that sort of, if that's a step region, is that expanding that way, or is it deepening?
It's both. If you look, oops. So it's definitely become wider. Here you can see this sort of new area, but it's also become deeper, in particular here. And there was another example where it's mostly become deeper, not so much wider in that place. So it seems to vary a bit.
The double convection for the shear-driven wind, but going back to your previous question, could you have mechanical shear heating that would lead to ice melting? Could not the deformation that you image on the surface, could that be enough to melt ice? Because it's true that this wheel is shaped like fracture.
Yeah, we did compare to moorings that were outside the ice another set of years just to get some statistics. And if you look at the heat energy that's transported in, that if you assume all that goes unhindered straight into the cavity, that would be enough to melt, I don't remember, 20 meters or so. So that could explain it, but we don't know. Is this answering the question?
Well, you talk about the ocean side, but I was thinking of the ice itself.
Oh, the shear in the ice. I see, whether that can be, that, yes, that's a really good question. That's a very nice, yes, I have not thought about that. I don't think anyone, it should be possible to calculate, I think. you know, the deformation and yeah.
The dissipation rate happens in rocks sometimes.
Yeah, and there was another paper quite recently also about the integrity of ice. And they showed, my understanding was that when you add water to ice, the integrity, its strength becomes smaller. So there could maybe be a combination. Maybe it's easier for the ice to, it sort of breaks up rather than melts. I don't know.
So you did mention double diffusion. Do you have measurements of the temperature and salinity?
We have one. Yeah, we have one. This is from that. Let me see here. The orange, I think, is from the drill site. We have one hole. They put down the instruments and then back up. That's what we have. And then we have all the colored other ones that is from the AV when it dives down and then goes up. So we have a few. It's not really casts, but this is what it looks like. And if you look carefully, you can, this one, for example, and in that drill site, you can see a bit of layering, some steps. But yeah, you often see that in connection. It does not mean that it is convecting. Actually, it does not even mean that it has been convecting, but it doesn't rule it out. Anyway, if it was completely smooth, but it's not. It's more. There are some steps. Yeah.
I have two questions. One is there any further ice?
We don't know, unfortunately. There could well be, in particular, inside the fractures. I think that's typically, if you have some fractal ice, it will get moved along and then it can suddenly float up. But we only get, and one other worry that we had was that maybe all is fractal ice. Maybe we are just seeing the edge of some fractal ice being moved around by ocean currents. That could explain why we have these steps. But then when we came back 2 years later, so then that means we are quite certain this is something solid that we are measuring. And we also had some overlapping lines where we could also see there, it doesn't change enough in 1 week. So we think it's ice and yeah. Not many answers, I'm sorry.
And then, sorry, the other one's actually about what's the baseline measure the height of the ice shelf from?
It's a sea level. So we measure the pressure of the, relative to the sea surface, the pressure of the lower edge of the ice, so to say.
So is that relying on the navigation of the AV?
The AV measures pressure. So the big unknown is the sound velocity. And in particular, if you have a very long range, you can introduce some, but you would spot those errors when you go back in the overlapping. So we think it's quite okay.
So I think we're doing quite well with time. Just looking at one more online question.
Yeah, now I understand. So when we measure basal melt, we have always in the past measured the vertical movement of the base. When you do satellite altimetry, look, you get the number you get is the vertical movement of the ice. So if you, for example, if we have a channel that becomes wider, it will look like a very big change, but actually it's a small change in the horizontal. And what you, because here we have some big gradients, for example, in the fractures, you have it's a vertical wall. And really what you should do is to reprocess basal melt. What we mean with it is ice melt, how much ice has melted in this thing. And that is perpendicular to the ice surface. So really, when you have dramatic topographies like this, you should change coordinate system so that you always calculate it. And there was a student that worked with this and looked closer at the fractures, and she did that conversion, and it turned out to be actually quite, she got the same number, she got 10 meters, that was in the West, 10 meters per year. In the traditional way, it was a big, up and down. But when she converted it to local coordinates, she got 10 meters. So in that region, it worked quite nicely. And no one has done it. We could do it. That's a good suggestion to do it for the 24 data where we can compare. Yeah, I think it's going to be bigger, but yeah.
Okay, might leave it there. There's do stay around for tea and Vicky's, I think, that are happening. But Anna is here until middle of March. So get in contact if you want to catch up a little bit more. And you're always welcome to come down and see the experiments in the lab. But
yes,
again, Anna.
Thank you. Yes.